Hello, welcome back, everybody. We're very pleased to have as our next speaker Miklos Rácz, who will be telling us about the largest common subtree of uniform attachment trees.
Okay, hello everyone, and thanks very much to the thanks very much to the organizers for organizing this wonderful workshop and the whole event. It's my second time in Brazil, first time in Rio, so it's great to be back and also great to explore Rio. So I'll be talking about the largest common subtree of uniform attachment trees. And I thought it's particularly appropriate to talk about this project here because this project started 2 years ago at the RandNET workshop in Eindhoven. It's one of these open problem working sessions that evolved into this project. So this is joint work with Johannes Baumler, who is now a postdoc at UCLA, Bas Lodewijks, who's a postdoc in Augsburg, James Martin, who's at Oxford, Emil Powierski, who's a grad student at Oxford, and Ani Sridhar, who's a postdoc at MIT now. So let me tell you what the problem is. And so this talk will be about uniform attachment trees, also known as uniform random recursive trees. So on Tuesday, Luc already told you, a lot of things you have to know about uniform attachment trees. So this will not be a foreign object anymore. So let me just still define it and tell you what we'll be looking at here today. So we'll be looking at randomly growing trees, the simplest of which is uniform attachment. So you start with a single vertex, and then you add vertices one at a time, and you connect them with a single edge to the existing tree that you have. And you do this in a way where you pick the node to connect to just uniformly at random. Right? So the simplest possible model, really, of a randomly growing tree. There are variants and other models you can consider, like preferential attachment, where you attach with probability proportional to the degree of the existing vertex. Or you can more generally attach with probability proportional to some function of the degree. And there are other variants you could consider. And we'll briefly talk about some of these, but mainly we'll focus on uniform attachments. OK. And by the way, feel free to stop me anytime throughout the talk if you have any questions. OK, so we'll be considering the largest common subtree of uniform attachment trees. So here are two uniform attachment trees. And, well, a common subtree is just a subtree that is just a tree that is a subtree of both of these trees. OK, so in this example, you have two uniform attachment trees, and this orange tree is a common subtree, and in fact, it's the largest common subtree. OK, and what we'll be interested in is what is the size of this largest common subtree. OK, so we'll denote this by x sub n. This is the largest common subtree of two independent uniform attachment trees, Tn1 and Tn2. OK, and so in this example, these both have 1,000 nodes each, and the largest common subtree has size 484. So it's pretty sizable. OK, any questions? This is the central object of the talk, so if you have any questions. So these are unrooted, unlabeled. So when you run uniform attachment, there's a natural root, the first vertex, and there are some natural labels, right? A vertex is labeled by the time when it was born. But here we're going to forget the root and forget the node label. So these are just unlabeled trees, and we're just interested in the largest common subtree of these unlabeled trees. So yeah, that's a very important point. Any other questions? OK. And so later I'll talk a bit about motivation, where this comes from, what are various reasons why we might care about this. But I think this is also just a very simple and fundamental mathematical object, and so it's worthy of study just in its own right. So for now, let's just take this problem as granted, and let me just tell you about our results. And then I'll talk about motivation and related work a bit later. OK, so our main result is a lower bound that says that this largest common subtree has size at least n to the power of 0.83. And so I'm going to tell you three different arguments of lower bound arguments. They're increasingly complex and give increasingly better bounds. So I will tell you about a simple bound that is just a simple recursive argument. And this gives you a polynomial lower bound already, but it's relatively small. It gives you something like n to the 0.32. Okay? Then I'll tell you a construction, and I'll call this the Ulam-Harris common subtree. I'll explain what all these words mean, so don't worry if these are foreign at the moment. But it's a particular construction of a common subtree. And we can analyze this. And this gives a lower bound of n to the 0.828. This is 2 times the square root of 2 minus 1. Okay? And then I'll also tell you how you can kind of locally improve this construction and go beyond this power to get 0.83. So here, the jump from 0.828 to 0.83 is quite minimal, but the point here is more the qualitative improvement of going beyond this particular construction. Okay. Any questions? Okay, so these are lower bounds. What about upper bounds? So unfortunately, in terms of upper bounds, we have some results, but they're, in some sense, a bit embarrassing. So on the one hand, we can show that with high probability, and for me with high probability here means just with probability tending to 1 as n goes to infinity. So xn is less than 0.999 times n. Okay. Okay. So what this means is if I look at the fraction of vertices in the largest common subtree, this is bounded away from 1. Okay. This is kind of a union-bound argument. I won't really talk more about this. And then we have another type of upper bound, which is the following. So if I fix epsilon, and I look at the probability that the largest common subtree is less than epsilon times n, so relatively small on a linear scale. So this fraction is small. Then this has probability at least delta, strictly bounded away from 0. Okay, so what this means is that xn over n is not bounded away from 0. Okay? And the proof of this is actually via a nice construction, and this connects to the sizes of subtrees below a root, which are given by a stick breaking process, which Luke already told you a lot about. So I'll explain this in a bit more detail towards the end of the talk. Any questions? Okay. So, the main question is, what's the truth? What is the order of magnitude of the size of the largest common subtree? Well, we don't really know. So we conjecture that it's, n to the 1 minus little 1. So the power should be 1, but, it might, it's like roughly linear, but it might not be linear. So, we don't really know. And, amongst us also, opinions may vary a little bit in terms of what the right order of magnitude is. In any case, here are some simulations. Okay? So in black, so here, these are results of, on the horizontal axis is the number of vertices, and the vertical axis is the size of the largest common subtree, or the size of the common subtree for various constructions. And in black, so it's not quite the largest common subtree. So I should add that, in general, if you want to compute, if you have two graphs and you want to compute the largest common subgraph, that's a hard problem. Okay, so that's a hard problem. But if you have two trees, then there are nice polynomial time algorithms. Okay, so that's great. Here, what we do is we look at we have the two trees and two uniform attachment trees, and we're going to match the root node in one to the root node of the other. Okay, and we're going to look at the largest common subtree with this restriction. This makes the computation a bit faster, and we think that this shouldn't change much significantly. in terms of orders of magnitude. So this should hopefully give a good idea of what also the order of magnitude is for the largest common subtree. The computational barriers are not vast. So like, if someone really, put a gun to my head and said, show me plots for the longest common subtree, you could do that. But, it requires a bit more. Uh-oh. Sorry about that. Okay, so this is how the root-to-root largest common subtree grows. I told you about this second construction, the Ulam-Harris common subtree. In red, that grows like here, and if with some local optimizations, you can improve that a little bit. Okay, so if you look at a log-log plot, the slopes for the Ulam-Harris subtree are like 0.81, and for the local optimization, it's 0.83. So it's relatively well matches the theoretical results. And for the root-to-root largest common subtree, it's roughly 0.9. So these can be viewed as some kind of empirical lower bounds. And any questions? Okay. You can also plot, a histogram of I think this is 10,000 simulations or 1,000 simulations of the largest common subtree with n equals, so 10,000 vertices each. And from this, what you kind of see is that if you normalize xn by the expectation, then it seems like there's a non-deterministic or random limit for this. Okay, but we're far from showing something like that. Question?
So I assume that you try to show concentration and it doesn't. That's evidence of lack of concentration.
So the variance is kind of on the order of the standard deviation is on the order of the first moment.
By experiments.
By experiments, and it seems like also via by experiments certainly. Any other questions? Okay, so this is the main conjecture. Let me say that the methods, we'll focus on uniform attachment, but the methods do go beyond that. So for instance, let's consider this more general model. If you attach with probability proportional to some function of the degree of the existing node. Okay. So under mild assumption, so if this function grows at most linearly and it's bounded away from 0, then this recursive argument, which I'll tell you later, it's simple and it just works broadly, and it gives you a polynomial lower bound for the size of the largest common subtree. So for more general models, there's also a different kind of very trivial lower bound, which is just let's take the maximum degree in the two trees, or two graphs, and let's take the minimum of those two. Well, the largest common subtree is at least the minimum of the two maximum degrees plus 1, simply because you're going to find a star of that size in both trees. Okay. So this is kind of trivial, but on the other hand, it does give you reasonable bounds in some cases. So for instance, if you look at affine preferential attachment, so this function is n plus some constant, then depending on what this constant is, sometimes the recursive argument is better, sometimes the maximum degree lower bound is better. Okay. You can also consider models that don't fit into this, don't fit these mild conditions. For instance, superlinear preferential attachment, which Roberto analyzed and characterized in great detail with Joel Spencer. So there, there's a kind of a super hub vertex emerging, which has a very large degree, and that you can analyze very precisely, and that tells you that in that case you can really nail down the largest common subtree, the size of the largest common subtree, but it's basically because this has a very special structure. Any questions? Okay. So I'll tell you about some proofs for the results, but before that I just want to tell you a bit about some motivation and some related work. So how did we start to think about this? So one motivation comes from graph matching. So let me tell you a bit about graph matching. So this is a fundamental problem. So here we're given two graphs which are similar, we think, and we want to figure out a good matching of the two sets of vertices that shows this similarity. Okay? So maybe in these two, with these labelings of the two sets of nodes, so this gives you a matching, and then you have a bunch of edges that are in common and some that are not. And the typical objective that you want to maximize in graph matching is the number of common edges. So that's something you want to maximize. Now, this is hard in general. So that's an issue. But at the same time, graph matching does arise in a bunch of applications, and where this task is solved effectively. So some examples are in social networks. So you have, for instance, two different social networks, and you want to map users in one social network to users in another. In computational biology, maybe you have two protein-protein interaction networks, and you want to integrate information from several of these for improved understanding of the underlying biological networks. It also arises in computer vision. So in computer vision, also often you have some object, and how you keep track of that is via some kind of mesh, kind of triangular mesh. And then if you have a video, well, this object moves in the different frames of the video, and you want to keep track of the object. Okay, so effectively what you have then are various random geometric, some kind of geometric graphs, and you want to match them across frames. Okay? So these are some applications, and in practice this often works very effectively. So we want to understand why is this so. And it's partially because often real-world networks are not worst case. So one natural thing to do is to try to understand graph matching in the average case. Okay, so on various random graphs. So a natural model as a starting point is the so-called correlated Edersheim model. So it's very simple. It was introduced by Pedersani and Grossklauser in 2011. So start with an Edersheim graph, GMP, parent graph, and then subsample the edges with some probability S, okay, to get a graph G1. So every edge that is there, you keep with probability S independently, and non-edges remain non-edges. Okay? And you do this a second time as well. Okay? So then you have two graphs that are both marginally Edersheim with probability P times S. And if you look at corresponding edges across the two graphs, they are not independent, but they are correlated. Okay? And the correlation is roughly S. It's not exactly S, but roughly S. So, and then what you can do is suppose you randomly permute the node labels in one of the graphs. And so the goal is to find this random permutation that really recovers the true latent alignment of the nodes, two sets of nodes. Okay? So this is a fundamental problem, and this has been very well studied in the past 5+ years. So now a lot is known about this. So the fundamental information theoretic limits of when you can do this, when you can't, are pretty well understood. There are a bunch of works that were pushing to understand not just the information theoretic limits, but to find efficient algorithms for graph matching. And there were some recent breakthroughs a few years ago, particularly by Mao, Rudolphin, and Tikhomurov, and Mao, Wu, Xu, and Yu, who found efficient graph matching algorithms in the setting where S is bounded away from 1. So this S correlation parameter, if you set S to be 1, then the two graphs are just, well, they're both the original graph. So that's the graph isomorphism problem. Okay? And as you move S away from 1, you can think of 1 minus S as the noise level of the problem. Okay? And so these works that I just mentioned, they developed efficient graph matching algorithms in the setting where the noise is bounded away from 0. Okay? And these actually have very interesting connections with combinatorics and trees. So for instance, there is a conjectured information computation gap at a particular level of this correlation. If there's time later, maybe I can talk about it. So at s squared equal to alpha, where this is Otter's constant, which is probably familiar to some of you. If you look at the number of trees on unlabeled, unrooted trees on n nodes, they grow roughly like alpha to the minus n. Okay, and this is like 0.338. Any questions? Okay, so it's very important to understand, the most fundamental model, which is correlated error training. But at the same time, Keith and Dieter, as they mentioned in the short courses, error training. Oh, I'm sorry. I don't know why this keeps happening. So you also want to move beyond error training and to understand graphs that have some kind of structure. So there's a increasing amount of work that's trying to go beyond correlated error training and understand various correlated random graphs with structure. So there's an increasing amount of work on correlated stochastic block models. So the model you can think of as the same kind of subsampling model, but you start with a stochastic block model. Okay? And so I talked about this 2 years ago in Eindhoven. You can use graph matching to improve various community recovery algorithms. So that's one kind of application where graph matching can help. We also have a work with Ani on correlated randomly growing graphs, a particular model. If someone is interested, I can tell you more about this model. It's different than the model I talked about on Monday, and which I'll talk about in a second again. There's also some works on correlated random geometric graphs. I know there's plenty of people here who work on random geometric graphs. Here there is a bit of a gap in the understanding, so I think there's definitely lots of room to better understand correlated random geometric graphs and graph matching in the geometric setting, if someone is interested in pursuing that kind of direction. And we also considered correlated inhomogeneous random graphs, so you can consider all kinds of models. Okay, now a particular model that I think is simple and interesting is the one I told you on Monday about. So here, we have two uniform attachment trees. That's the simplest model. And they're correlated through time. So at each time step, you either pick the node to attach to in an aligned way. So you attach to the node with the same label with probability alpha, or you do this independently. Okay? So that's the model. You have these aligned choice steps throughout the time evolution of the two trees. And so, then the most fundamental question is, can you distinguish a pair of correlated trees that are grown in this way from two independent uniform attachment trees? Okay, so this is a simple hypothesis testing question. And so, if you want to understand this, you want to understand the total variation distance between these two distributions on pairs of unlabeled trees. And so the conjecture, which I told you about on Monday, is that for any positive alpha, you should be able to distinguish. So this total variation distance should go to 1 as n goes to infinity. And so one challenge is that this aligned choice is really through the labels. And then once you have unlabeled trees, this can make the unlabeled trees go far apart. So this is one example. 3, 1, 2, 3, 2, 1, both are just a path of 3 nodes. But now vertex number 4 connects to vertex number 1. Then here, this becomes no longer a path. And here, this stays a path. Okay? So where one possible way to distinguish one candidate statistic is the size of the largest common subtree, right? Because the size of the largest common subtree, in some sense, measures how similar two trees are. Okay. So this is a natural candidate statistic, and this is kind of where this question came from. And so, of course, if you want to understand this statistic, you also want to understand it under the null model, which is independent uniform attachment trees. Okay? Now, the results I told you about are far from saying anything about this, unfortunately. So, we're not there yet. This doesn't mean that, this is not a good candidate as a distinguishing statistic. It may be, it may not be. We just don't know. And I should also say that, I mentioned this as an open problem. I don't want the lack of, this being, a lack of knowledge about this candidate statistic deter you from approaching this conjecture. Maybe there's just a completely different approach, a different statistic that, works magically and beautifully and simply to distinguish. Okay, so, part of why I propose the open problem is for you to come up with a completely different statistic that has nothing to do with what I'm telling you about. Okay, any questions? Yes?
Do you believe that the positive alpha, the largest common subtree, is linear?
Not clear. Yeah, it's not clear. Yeah, I would love to understand this also for the correlated case. The simplest thing is just through the aligned choice steps, you get naturally a common subtree. But that just gives you something like n to the alpha or something like this. Yes, question?
Have you explored the properties of this test statistic or an approximation thereof in simulations?
Sorry?
Have you explored the properties of this test
Oh,
statistic?
yes, yeah. In simulations, it does seem like for the correlated trees, it is larger. Yeah, so simulations are promising that this could be useful. Okay, let me tell you. So this is a particular specific motivation. Let me tell you about some, a broader picture of where this fits in. So if we think about, probabilistic combinatorics, we study various combinatorial structures, and we often study what happens if we pick some kind of distribution over them. So one natural thing you can do is to take two such structures. This could be a graph or a permutation or a partial order or a sequence or a cladogram. Your favorite combinatorial structure, pick two of them, maybe randomly according to some distribution, and look at the largest common substructure that they induce. Okay? And here, there could be, depending on the situation, these could be labeled or unlabeled, and both could be interesting. Okay, and this general open problem was popularized particularly by David Aldous, who has a nice little survey on this. And so let me tell you some particular examples. Adder-Shrinian random graphs. So if an Adder-Shrinian random graph is labeled, then this is easy. So this is a quick exercise that you can do until the end of this lecture if you're bored. That's easy to understand. If Adder-Shrinian random graphs are unlabeled, in the dense case, you would think that this was solved 50 years ago or something like this. But actually, there's some work by Chatterjee and Diaconis, and also by Surya, Warnke, and Zhu on this from last year. And there, they actually have some very precise results, like 2-point concentration type of results, which really leverage the fact that you have lots of independence that you can work with here. Another example is, suppose I have two sequences, and I'm interested in their longest common subsequence. So this is a very widely studied problem because it's super important in computational biology if you want to compare two DNA sequences. Okay, and here also the random case has received lots of attention because, in the limit, these so-called Shweta-Sankov constants appear, which, to this day, we don't know what they are. In fact, I think on the archive, there were just like, in the past month, there were some new works getting improved bounds on these constants. So another story is that of cladograms. So these are leaf-labeled binary trees. Okay, so suppose you have a binary tree like so, and you have labels on the leaf. Okay, so this, the motivation here comes from phylogenetics. So you can think of these as species, and this binary tree represents, how they evolved. Okay. Now, so I want to tell you a bit about the story around the largest common subtree of random cladograms, because this also has received some attention recently. So, why is this interesting? So here, the motivation comes from phylogenetics. So suppose that you have two phylogenies of various species. So maybe this is, maybe you have some host species and some parasite species. And so you have a phylogeny for the host species, and you have a phylogeny for the parasite species. And, depending on how close they are or not, this can tell you a lot about how the host-parasite associations and interactions, those evolved over time. Okay? So understanding this, and how close two phylogenies are, one way to measure it is through the largest common subtree. Okay? And here, this is an example where the labels matter. So this is a labeled case, and you want the largest common subtree in a labeled fashion. Okay. So here, too, you want to understand this in general, but in particular, if you want to do statistics, you want to understand the statistic under the null distribution, which is just two independent random trees. And so that's what a line of mathematical work has been exploring, starting with Aldous, who conjectured that the size of this should be n to the gamma, where gamma is some constant strictly less than a half. So there have been several works. So Bryant, McKenzie, and Steele, around 2003 when this work started. So kind of a first moment bound gives you n to the half. Then there was a work about 10 years ago, n to the 1/8 lower bound. Aldous proved n to the 0.36. Caselli proved n to the 0.44. And then just very recently, Budzinski and Sinizerg, they proved, they broke this square root n barrier and proved an upper bound of n to the half minus epsilon, where this epsilon is something really tiny. Okay, so this is, again, kind of a bit reminiscent of the graph matching story that I told you before. Here's a problem motivated by some actual application, and then the problem turns out to be hard, but there's lots of interesting mathematics behind this. So, I won't tell you anything about the mathematics behind this, but there's lots of interesting mathematics here. You can imagine that this has something to do with the continuum random tree, just because, it has connections with all this, and so there's lots of interesting connections here. Yet, the results are so far, they're not able to reach a level where they can have an impact on the application yet. Any questions? Okay, so then let me turn to back to our main subject, which is the largest common subtree of two independent uniform attachment trees. And let me just tell you a bit about the proofs. Okay. So this is just a reminder. We want to prove this lower bound, n to the 0.83, and I'll give you three different arguments, starting with the simple recursive argument. So how does this argument go? So let's look at the evolution of a single tree from time n to time 2n. Okay, so this is an example here. And let's look at a particular vertex in the tree at time n, vertex v, and then let's look at what happens until time 2n. So the probability that no edge attaches to this vertex, so it gets it's avoided by everything that comes in. This is just, the first vertex coming in has to avoid it. That has probability n minus 1 over n. The second vertex has to avoid it. That has probability n over n plus 1, and so on. So you have this telescoping product or this product where everything cancels. So what you get is n minus 1 over 2n minus 1, which is less than a half. Okay? This also means that the probability that some edge attaches to this vertex is at least a half. Okay? Now, I argue that this implies that if we look at the size of the largest common subtree, let's say an expectation, it's simpler that way, then if we go from time n to time 2n, then this expectation increases by a factor of 5 over 4, okay? At least. Why is this so? Well, at time n, you have the two trees, and you have some common subtree. Okay? Now, every vertex in that common subtree, in both of the trees, it has an incoming edge until time 2n with probability at least a half. So for this vertex, the probability that you have an incoming edge in both of the trees is at least a quarter. Okay? So in expectation, a quarter of the vertices in the common subtree will have an additional edge coming to them. And then that's, if you take those edges into the common subtree, that gives you a larger common subtree. And you've exactly grown by a factor of 5 over 4. Okay? Any questions? So then you iterate this, and you get that the expectation is at least n to the log base 2 of 5 over 4, which is like n to the 0.32. And, you can optimize this argument by not looking at time n and 2n, but n and some constant times n. But you'll only get up to something like n to the 0.33. So actually, the choice of a factor of 2 is actually close to optimal. Any questions? OK, so let me tell you about the Ulam-Harris common subtree. So this is a particular construction. So before I do this, I have to tell you about what an Ulam-Harris tree is and what are Ulam-Harris labels. So this is the following. So suppose you have, so the Ulam-Harris tree is a tree which is an infinite rooted and ordered tree. So you have a root on top, and then the root has countably infinite children. These are labeled 1, 2, 3, etc. And they're also ordered in the plane. Then each of these children have countably infinite children. And if you look at, say, the children of 2, they are labeled 2, 1, 2, 2, 2, 3, etc. Okay? And then you go on. The children of 2, 3 are called 2, 3, 1, 2, 3, 2, 2, 3, 3, etc. Okay, so I hope the labeling is pretty self-explanatory. And so then if you have a vertex in the Ulam-Harris tree, then this Ulam-Harris label, it tells you about the genealogy of this vertex, right? The last coordinate, it tells you, which child am I of my parent, and so on. Okay? Now, the natural notion of depth in the tree is the distance from the root. Okay? So that's just, using the Ulam-Harris labels, that's just the L0 norm of the Ulam-Harris label, how many coordinates it has. There will be another notion that is a bit similar to depth that will be important for us, which is the L1 norm of a Ulam-Harris label, so just the sum of the coordinates. And we'll call that the level of V. In some sense, it would make sense to call this also the depth of V, but the depth is already taken, so we'll call this the level of V. And a simple, you can convince yourself that the number of nodes at level n is 2 to the n minus 1. Okay, so in this picture, for instance, the nodes at level 3, you have 3. Then you have 1, 2, 2, 1. Excuse me. So you have 3, 1, 2, 2, 1, and 1, 1, 1. Right, so that's 4. So you can, you maybe see the pattern of binomial coefficients here. OK. Any questions about the Ulam-Harris tree? Okay, so now suppose you have a randomly growing tree in general, but let's think specifically about a uniform attachment tree. You can think of it as, there's kind of two perspectives. You can put the initial node here, and then the first node, when it attaches, you put it here. The second node, if it attaches to the initial vertex, you put it here. If it attaches to the second vertex, you put it here, and so on. So you can view a uniform attachment tree as a random subtree of this Ulam-Harris tree. Or alternatively, a slightly different perspective maybe is that the Ulam-Harris labels are random labels for your uniform attachment tree, for the vertices of your uniform attachment tree. Okay. Okay. Now, once you have these labels, a natural thing to do is, so here are two different trees. Within the vertex, I have the original node labels, so the time when they were born. Okay? And now, I also have in the brackets the Ulam-Harris labels. And then now you have two trees. They will have, typically different Ulam-Harris labels. And you can look at the Ulam-Harris labels that appear in both of the trees. Okay, so those are these red subtrees. Okay, the root, 1, 2, 1, 1, 1, 2. These Ulam-Harris labels appear in both trees and no other ones. And the induced subtree will give you a common subtree. This is not too difficult to show, and I hope this example already illustrates this. Okay, so this is a natural construction, and we want to understand what does this give. Any questions? Okay, and so you can analyze this, and what you get is that this gives you n to the 2 times square root of 2 minus 1, minus epsilon, say, with high probability. And this gives you the n to the 0.828. Okay? This gives you with high probability, but let me tell you, why this holds in expectation. So first of all, if you have, what is this quantity? So this is just I sum over all vertices in the Ulam-Harris tree, and I want the vertex I to be in the first tree, and I also want it to be in the second tree. Right? So now, if I take an expectation, then this is just a sum over all vertices in the Ulam-Harris tree, and by linearity of expectation, and then also by independence of the two trees, this is just the probability that vertex I is in, say, a single tree squared. Okay? So, this is the fundamental quantity that you want to compute. And, we'll further lower bound this by just looking at vertices at a particular level n. Okay, where we're going to choose this level appropriately. Okay, that this is the the right level that optimizes this thing, and once you do this, you see that this is actually the key property is that, which I didn't tell you here, is that if you view the uniform attachment tree as a random subtree of the Ulam-Harris tree, then before a particular node in the Ulam-Harris tree is born, you need to have at least the level of v many bursts happen in this process. Okay? So in particular, what this means is that for nodes at a particular level, all of these probabilities are the same. So this is just 2 to the n minus 1 by that comment over there times the probability that this node is in the tree at time n squared. Okay? Any questions? Okay. And then we'll have to do a large deviations analysis to optimally choose capital N. And it turns out that we'll choose n to be capital N to be little n to the square root of 2. Okay. Any questions? Okay. So, once it comes down to analyzing these things, it's useful to look at a continuous time perspective. This is pretty standard, so I'm sure many of you have seen this. So instead of looking at the evolution of the tree in continuous time, adding one node at a time and one edge, you can look at this in continuous time. So in a yield process, you start with a single individual at the root, and then each individual gives birth repeatedly at rate 1. And then whenever any individual is born, it again starts giving birth at rate 1. Okay? So then what this corresponds to, if you're exploring this Ulam-Harris tree, and on the edges you have IID exponentials with rate 1, and the clock for a particular edge starts ticking once everything before it has been born. Okay? So in this perspective, the probability that a particular vertex, when is it born? Well, the distribution of the time when a particular vertex is born is exactly given by a sum of IID exponentials with rate 1, where the number of summons is exactly the level of V. Okay? Okay. And then, so there are some standard known results of how to transfer the continuous time perspective to discrete time. So the Yule process grows at an exponential rate. And if you look at the Yule process at the stopping times when you have exactly n vertices explored, then the distribution of the resulting tree is exactly a uniform attachment tree. Okay? So then, if you analyze the continuous time process and you look at the largest common subtree at time t, and that grows like at least f of e to the t, then that gives you, for the discrete time process, a lower bound of f of n. Okay? Okay. So then, essentially, what you have to do is analyze, the levels of the Ulam-Harris tree. And, okay, so essentially what you have to do is, by this calculation, this is the quantity you have to optimize over alpha greater than 1. And so this is a large deviation calculation. And this is nice because we know, for exponentials, we know the large deviation's rate function, so this is pretty explicit. Okay, so you can optimize this, and it's optimized at alpha equals square root of 2. And yeah, then this gives the lower bound that we talked about. Okay? There are other interesting choices to consider. So if you look at not level square root 2 times t, but t, that's when all the nodes are born. At that level, all nodes are born with some probability roughly a half. Okay, there are other interesting levels to consider. Okay, but why isn't this optimal? One particular reason. What we're doing here is we're essentially matching early vertices, right? We're matching the two roots in the tree, then we're matching the first the second nodes to each other, etc. So we're matching early vertices in the two trees. But the thing is, if we look at how these trees grow, there are fluctuations in how quickly different parts of the trees grow. Okay? So that's one particular reason why this is suboptimal. So we wanted to at least push beyond that. And what is, how can you push beyond that? Let's consider the setting where, so this is the root, then this is vertex 1, vertex 2. And what if this node 2 has a child before node 1? Okay? So that means that this subtree is growing faster than this subtree to the left. So one thing you can do here is then let's switch the subtrees. Okay? Let's switch the subtrees, and then we're going to match. You're still going to get a tree that is isomorphic to the original one, so it still has the same distribution. But this essentially it's a different way of matching the nodes across the two trees. Right? Okay, so what does this give you? Well, originally you had these IID exponentials on these edges. And what this gives you is, well, here, so this E1, the first exponential stays the same. And this exponential E11, oh, I'm sorry. So this E11 exponential is replaced with the minimum of E11 and the sum of these two exponentials, E2 plus E21. Okay, and this is smaller. Of course, there's no free lunch. Once you do this, the passage time here on the right will be longer. Okay, but in general, you still win a bit. Okay, and so originally, the time when a vertex was born was distributed as a sum of IID exponentials. And now, after these switching operations, and we don't just do this at the root, but we do this everywhere. After doing this, the distribution of the birth time of a particular node in the Ulam-Harris tree will look like this. So you're going to have a sum of IID things, some of which are the minimum of one exponential and the sum of two other exponentials, some of which are a max, some of which are just simple exponentials. This is depending on your path, the path of a particular node from the node to the root. Okay? So for some vertices you win, for some you lose, but generally you win. And then you have to do a large deviations kind of calculation. The good news is that you can still explicitly calculate the rate functions, the large deviation rate functions for these kind of random variables. So that's the good news. The bad news is you can't really optimize them analytically. So it seems a bit hopeless, but you can still at least numerically almost optimize them, and you can get beyond what this gives. Okay? Any questions? Okay. So that's about the lower bounds. Let me quickly tell you about the upper bound. And so this is just that, if you look at xn over n, it's not bounded away from 0. So it can be like, xn can be like smaller than epsilon times n. And I'll just end with this proof by picture. So let's look at a tree, uniform attachment tree, and let's look at the subtree sizes below the root. So Luke already told you that these are given by a stick breaking process. Okay? So let's consider the event that all of these subtree sizes are at most epsilon times n. Okay? This has some constant probability that only depends on epsilon. Okay? Now, let's consider this other event where I have the root and then its first child and that node's first child, etc. And the property that I want to enforce is that everything that is over here, this subtree, has size at most epsilon times n. And similarly here and at every level. Okay? Now, by exactly the same kind of stick-breaking argument, this also has probability at least some constant depending on epsilon. Okay? So both of these properties hold with some constant probability. So now what if one of your uniform attachment trees looks like this and the other looks like this? So the claim is that then, well, the largest common subtree cannot be more than, well, some constant times epsilon times n. Why? Well, let's consider where this root node is mapped in this other tree. First of all, if it's not mapped, then the common subtree is contained in one of these small subtrees, which already has size at most epsilon times n. If we do map this root somewhere here, what's the situation? Then suppose we map it here. Then all of these dangling subtrees are small, and you can match one of them maybe with this subtree, and the other with everything here, and the other with everything here, but that's it. Because you don't have enough room, okay? So that's essentially the proof of this. Any questions? Okay, so thanks very much for your attention. I'm happy to take any questions.
Questions?
In this last upper bound thing, there seems that there could be some kind of recursion that you could use to try to do the upper bound. Have you thought about that?
A little bit, yeah. Yeah, it would be great to get stronger results, yeah.
Yeah. Yes. Wonderful talk. Wonderful talk. This improvement you have on the Ulam-Harris construction, you're using the binary tree view of the uniform random recursive tree, of course. And that's why you get. So what if you recursively at each level order by subtree size?
Like everything?
So you start at the root, you have two subtrees in the binary tree version of the,
Yeah.
and you take the largest on the left and the smallest on the right. And then you do recursively at every,
Yeah.
that should be even a bigger improvement than what you have, because you basically only do it at the first level.
Yeah.
It's equivalent to what you do, huh?
Yeah.
With
Yeah.
ordering the exponentials.
Yeah. Yeah.
It could give you even more, maybe perhaps going over, anyway.
Potentially, yeah. I mean, it would be great if we could analyze something like that. Yeah, I don't know how, would
But
these,
the analysis
would these,
might be actually easy, huh?
okay.
Yeah, okay.
Yeah, we should maybe talk after.
Because it's kind of structured and it's recursive.
Yeah.
Okay,
And
anyway.
so do you think these rate functions?
Pardon?
Do you think these rate functions would be computable in that case?
I think it would give you a better constant. We can think about it. Okay.
More questions? Okay, let's thank Mickey again.